I am Anil Kumar. Welcome to my series on trigonometry. In this video, we'll learn about graphing tangent functions and finding equation from the graph. You can always learn from me by sending an email to the address given here. You can always check my website for the new videos. This video could be long as we are going to discuss the characteristics of the tangent function. We'll also discuss transformations and find the image points by mapping. Graph of transfer functions, how do we do that? Will be discussed in great details. How to write equation from the given graph. We'll be working with both degrees and radians and end up with a test example. So there are about 7 examples which we'll be talking about. Here you see a tangent function. It is always increasing between two vertical asymptotes, as you can see here. 3 critical points will be considered. One at the origin, which we will call as point B for our discussion. The other one will be at 45 degrees, y value being 1, and then another point at minus 45 degrees, where the value is minus 1. So these are the 3 points which we are going to consider most of the time, where point A on the parent function will be at 45 degrees 1, B will be at 0, 0, and C will be at minus 45 degrees minus 1. Right? In case you're working in radius, then remember that pi is equal to 180 degrees. So when I say pi by 2, it is going to be 90 degrees, and pi by 4 is 45 degrees, correct? Of course, 2 pi will be 360 degrees. Also remember that period for the tangent function is basically pi or 180 degrees, correct? So when we say period, in that case, it is the distance between, I can say the value between the two vertical asymptotes, right? So this is what which repeats, right? This is pi, you can say this value, correct? So the period, let me write down here itself, is uh, between vertical asymptotes, right? Let me write vertical asymptotes as VA. As you can see here, the vertical asymptotes are at minus 90 and 90. So it could be 90 degrees minus of 90 degrees. That gives you a period of 180 degrees, correct? So that is for the function y equals to tangent x. So that is how you will do uh, get all the parameters for your parent function tangent x. Now this particular way which I'm showing you in between, the very first one will also be called as the principal tangent function, which can be repeated since these are all periodic functions to get the graph in the entire domain. Of course, the domain will not include the vertical asymptotes for the function. On the right hand side, we have a transformed function, correct? Now, this function is transformed, as you can see that the points A, B, and C have been shifted. You can say that point A is now at y equals to 2, so we'll refer them as A dash. B is shown here, we'll refer that as B dash. And C, you can say C dash or C prime. So these are your image points. Let me write down a different thing. These are your image points. Now, the distance between A and B has increased. You call this as stretch, right? So you can clearly see that the graph of the function on the right hand side is vertically stretched, right? So that is a kind of transformation which has taken place. So now let's begin and understand the characteristics individually and see how do we exploit them so that we could sketch very easily within no time the graph of tangent function and also write down the equation from the graph. Perfect. Let's begin with the properties themselves. So we'll talk about the properties of tangent function. So now, once again, let's look into the parameters. First one is always look at the vertical asymptotes, right? So at odd multiples of 90 degrees or pi by 2, the vertical asymptotes exist. And the reason is very simple because tangent x is basically sine x over cosine x, correct? Where cosine x is not equal to 0, it is in the denominator, correct? Now, zeros of cosine x are what? Right? So these values are basically, if you are writing in radians, you can write them as pi by 2, both plus and minus, right? Plus and minus 3 pi by 2, and so on. So these are odd multiples of pi by 2, right? Or 90 degrees, correct? So that is what we mean when we say odd multiples of pi by 2, correct? Or working in degrees, odd multiples of 90. So these are the vertical asymptotes. So let me mark vertical asymptotes here. So the vertical asymptotes are these, correct? Shown in red. So vertical asymptotes are odd multiples of 90 degrees or pi by 2. Domain does not include odd multiples of 90 degrees or pi by 2. Related statements, since the value of cosine x is 0 there, so that is not included in the domain of tangent function. So it is a discontinuous function. So one thing we learn about is it is discontinuous. Now, range is set of all real numbers. So as you can see here, the range is shown, the graph is moving from negative infinity to positive infinity as shown here, correct? So it is all real numbers. It is increasing throughout. So that is another very important characteristic. So we have understood these. Now it is always increasing in its domain as you can see from the graph. It has odd symmetry. So when we say odd symmetry, it means that tangent of minus x is equal to minus tangent of x. Perfect. So if you compare it about the origin, this is the origin, right? This is the origin right in the center, and any point on the graph has a image or diagonally across about the origin, as you can see, right? So that is the odd symmetry. Just as sine function. Perfect. Period of tangent function is 180 degrees or pi. So normally when a graph is given to us, we will we can find the period between consecutive vertical asymptotes. So in this particular case, as you can see, that the vertical asymptotes close by, one is at 90 degrees, correct? And the one before that is at minus 90, right? So minus of minus 90 degrees, that gives you the period, which is 180 degrees, right? That is what we mean when we say, if you want to check the period for a tan function, in that case, it is the difference between the consecutive vertical asymptotes, right? So we understood how do we find period from the graph. X-intercepts. So x-intercepts are when sine is 0, right? So this is when sine x equals to 0. So that is n pi, right? So we know sine x is equal to 0 when x is equals to n pi, correct? N is all integers, n belongs to integers, correct? Vertical intercept is at origin itself. When you substitute x equals to 0, we know tan 0 is basically equals to 0. Perfect. So that is how we will actually summarize the properties of tangent function. Now here is a very important activity for the students. I'll encourage them to answer this question. Explain why the graph of tangent function approaches positive infinity while approaching from the left side on 90 degrees and negative infinity while approaching from the right side of 90 degrees, right? So what we're trying to say here is that when x approaches 90 degrees from the left side, then y approaches positive infinity. And when x approaches 90 degrees from the right side, then y approaches negative infinity. Correct? So that is this particular line. As you can see here, clearly this is approaching positive infinity, correct? And on this side, it is approaching negative infinity, correct? This is the line where x equals to 90 degrees, correct? You can see nature of the graph. It is approaching positive infinity from the left side, right? And from the right side, it is approaching negative infinity. Okay. Let's move on and look into what is called a principal cycle, right? Principal cycle. So as you can see that the tangent function is periodic, right? So we have a periodic function. Now, in case of a periodic function, we first sketch, or you can also describe principal cycle, right? And rest is repeat the same. Correct? So that's the whole idea. So normally when we work on the periodic function, it is good enough to describe a cycle. And this cycle, when we are defining into one particular interval of our interest, we say that is going to be the principal cycle. So that is how we have got this term principal cycle. Now remember, tangent function has a period of 180. So we can graph a cycle in the interval of 180. So you can choose any 180 degrees interval and repeat it over the required range. At odd multiples of 90 degrees, the graph of the tangent function has vertical asymptotes. So we also know that we do have vertical asymptotes at, let's say here, minus 90 degrees, correct? And at 90 degrees plus. Now at odd multiples, the next will be at 270 degrees, right? 3 times 90 degrees. At odd multiples 90 degrees, the graph of tangent function has vertical asymptotes. So that is kind of important to understand. Vertical asymptotes means that when x is approaching a value, let's say a vertical asymptote is at 90 degrees, it means that when x approaches 90 degrees, then y approaches infinitely large value. What we have seen here, that when you are approaching 90 degrees from the left side, y is approaching positive infinity. And when x approaches 90 degrees from the right side, y is approaching negative infinity, right? So that gives us the discontinuity, right? So that is the discontinuity also. And we say this is discontinuous function. Perfect. So these are good points. Now tangent function is odd, so the interval between minus 90 and plus 90 is the principal value. Now it has an odd symmetry. You can see the graph of the tangent function as shown here. It is symmetric about the origin, right? It is symmetric about the origin. So since it is symmetric about origin, right? That is what we mean when we say odd symmetry, correct? So, so therefore, it is important to note that from minus 90 degrees to plus 90 degrees, we could consider one cycle and we'll call that cycle to be the principal cycle, right? So the principal cycle for tan x will be from minus 90 degrees to plus 90 degrees. So our principal cycle here will be from minus 90 degrees to plus 90 degrees, right? Those who are working in radians, they can say from minus pi by 2 to plus pi by 2. So that becomes our principal cycle. So now we'll consider the key points in this principal cycle. So let's go to the right hand side. So we'll consider the key points on the right hand side, which is here. Now here, the points are, we have a point which is 0, 0, right? And then we add, so we have mentioned here degrees. At 0 degree, 30 degree, 45, 60, and 90 degrees, we'll consider the key points. At 0, the value is 0. For 30 degrees, it is square root 3 by 3. For 45 degrees, it is 1. For 60 degrees, square root 3. But at 90 degrees, we have a vertical asymptote, right? So it approaches positive infinity. Since we are considering the graph between plus and minus, we'll focus on 90 degrees approaching from the right, left side, right? So in that case, it is approaching infinity. Now the function is odd, correct? Since the function is odd symmetry, we can find the corresponding points on the other side also, correct? So those are negative values of these. Perfect. So negative 30 degrees will give us negative square root 3 over 3. Negative 45 will be negative 1. Negative 60 will be negative square root 3. So what I'm trying to say here is this point here will be what? This point here will be negative 45 degrees and the y value being negative 1. Correct? It is symmetric to the point on this side where the point here is, we'll call this point as A, which is 45 degrees and the value is 1. So you can see that A and A dash, we'll call this as A dash, they have odd symmetry, correct? That's what we mean. We'll term the point at origin as B for most of the time, correct? Well, we'll call this actually a point C. Uh, so these are the 3 points which we will always consider for transformation of the tangent function, correct? So A, B, and C. B being the point which is originally at the origin, right? And A, you can see 45 degrees 1 means 1 unit away. So the value A1 helps us to find the transformed function's vertical stretch. Correct. Let's move on. When we say odd symmetry, it really means that tan of minus x is minus tangent x. If we're working in radians, those radian values are also given here. And you can see that the function is always increasing in a cycle, right? So always increasing in a cycle. So that cycle repeats for a periodic function. Perfect. Now, let's look into the transformations. We'll actually first focus on transformations without phase shift. So here we have y equals to a tan kx plus q. That means we're talking about without phase shift. If that is the case, then look into the parent function once again. Y equals to tan x will be the base for all transformations, transform tangent functions. Key parameters are the points which we discussed, A, which is minus 45 degrees minus 1, B is 0, 0, and C is 45 degrees at 1. Vertical asymptotes being at plus and minus 90 degrees, and therefore the period will be 180 degrees, the graph being increasing with odd symmetry, correct? So these are the characteristics which we just saw in the graph of the tangent function, one particular cycle. Clear? So let me rewrite these points here. So that will make, let's say we have this function tan x. So in the function tan x, we are saying the key points are A, which is 45 degrees 1, and then we have B, which is 0, 0, and C, which is minus 45 degrees minus 1, right? That is what tan function is, the key points. Good. Now let's look into the transform function, which is for us, uh, let me write down different ink, tan of A tan, right? So multiply by A, so vertical stretch, kx, right? So horizontally compressed by a factor of k and translated q units up, correct? That becomes your transform function. So if that is the function, in that case, the image will be mapped like what? So the x values will get divided by k, right? The y values will get multiplied by a and translated q units up. So plus q, correct? That is what the transformation will be. So on the critical points which we are talking about, look at these points. So let's begin with B. So the image B will be what? When I multiply 0 by 1 over k, we still get 0, right? So this point remains at 0. As far as the y value is concerned, multiplying by 0 gives you 0, but the value of q will come here, correct? Now let's see the point image for A. So in this case, the x value will be 45 degrees divided by the k value, correct? And the y value, 1, will get multiplied by A, and to this we are going to add q. As far as C is concerned, it is similar to A, the image point. So it will be minus 45 over K. So it's odd symmetry, you can see. The value of minus 1 indicates that the A value will get multiplied by minus 1, right? So it is minus A, and plus Q we will get, correct? So these become the transform point. Now here, it is very important to understand few things. First foremost, if I are looking into the graph of image, this is your transform function, then Q, point B, the center point, directly gives us vertical translation. The value of q, correct? And from here, what we can do is that the y values of a prime minus the y values of b prime is what? Is equal to a, a, right? Vertical stretch. So the difference in the y values, you can see, is a. So we'll get the parameter a also. How do we get k? The value of k is from the period. So let's look into this part. So we have understood how do we use these image points to get the value of a and also the value of q, correct? Okay, the vertical stretch and vertical translation is taken care of. Now, vertical stretch is by a factor of a, which is the difference in the y values of our point a and B. Horizontal compression by a factor of K. The horizontal compression really means that the X value will be X over K, right? So that is affecting the period, correct? So we get the period from K value, correct? So that is how we get. So let's understand how. Now that gives us the period. Let's see how. So we'll write the period here. Period will be initially we have a period of 180 degrees which we get by doing 90 degrees minus of minus 90 degrees, correct? Now if it is transformed, in that case both will be divided by k, correct? So what we get here is basically 180 degrees by k. Do you see that? So this is the change in vertical asymptotes, right? So we can say it is difference in vertical asymptotes which is going to give us the period. So period will be pi by k. Clearly, we could find the period from the vertical asymptotes. And if the value of a is less than 0, then the graph will be decreasing because that is reflection on the x-axis. Perfect. So that summarizes a very good look at the tangent function itself. Now note, tangent function increases from minus infinity to infinity. They do not have amplitude. We have used the lowercase a, the stretch factor, to signify stretch and the compression, right? So this is the difference between sinusoidal functions and the tangent function, right? So this is compared with sinusoidal functions. So in sinusoidal functions, there's a turning point. So we have amplitude. Here we do not have any term as amplitude. So in sinusoidal functions, you have seen we normally use capital A, signifying the amplitude, and of course also the stretch factor. Here we are using lowercase a to signify that it's not an amplitude. Okay. Now with that foundation, let's answer a few questions. Here's our example 1. The question here is, I'd like you to pause the video, read the question, and then answer it also. And then look into my suggestions. Describe the transformations of y equals to tan x to sketch a graph of the function which is y equals to minus 3 tan 2x minus 4. So we'll actually focus on the equation y equals to minus 3 tan 2x, right? Okay, let me write it clearly. Minus 4. And then provide the mapping for the image points. So first part is to describe the transformations, and that too in order, right? So in order. Order means you have to do vertical stretches and compressions first. So stretches and compressions and reflections should be followed by translation. That is the order. So normally I say you can always go from left to right. So we are going to describe our equation from left to right. So let's begin with minus itself. So what does this minus means? This minus means reflection on the x-axis. The next term here is 3. The 3 is a vertical stretch by a factor of 3. Then we have 2, the k value. Now 2 is horizontally compressed by a factor of half, right? That is what it means. Horizontally compressed by a factor of half. And then we have minus 4, means translate 4 units down. So that is what it means. Vertically translate 4 units down. So that is how we can describe from left to right all the transformations, and that is the order in which the graph can be sketched. Now, from here, the horizontally stretched factor also provide us with the period. So from here, this horizontally stretched, in this case compressed by a factor of half, gives you the period for the tangent function. So the period now is not 180 degrees, but half of 180 degrees, which is 90 degrees, which you can see, correct? So that is how we will do part 1, which is to describe the transformations. Now, let's look into part 2, which is the mapping of the image points. Now, from the particular equation given to us, the x values get changed by the horizontal stretch factor. So, if you're looking into x and y values on the tangent function, this is on tan x, correct? In that case, on the transformed function, what will these values be? The x values will be divided by k, correct? That is horizontally, in this case, compressed by a factor of 2. So I replace this k by 2. Do you see that? So it becomes x over 2. As far as the y values are concerned, they'll be multiplied by minus 3. So we get minus 3 times the y values and then translated 4 units down. So like this. So that becomes the mapping for the given case. So the mapping has been shown on this table. Do you see that? Now we'll take the key points which we have been referring to as A, B, and C. So in this case, the point A is 45 degrees 1, point B is the origin, and C is minus 45 degrees minus 1. The images will be A dash, B dash, or B prime, C prime. So when you do half of 45 degrees, you get 22.5 degrees, correct? So that is important. And when you do 3 times minus 1, rather in this case minus 3 times minus 1, you get plus 3. And plus 3 minus 4 is minus 1. And so we get the value which is minus 1 here, correct? When you multiply by 0, minus 3 gets 0, but minus 4 is retained, correct? So minus 4. You can now notice that minus 4 in this case indicates the vertical translation, correct? Do you see that? So minus 4 is also the value for Q. So we know Q equals to minus 4. The value of A will be 22.5 minus 7. And the value of A is minus 7 minus minus 4. Do you see that? That gives you minus 3. So difference in the y values of these two consecutive points of our interest, key points, consecutive key points, help us to find the value of A. Perfect. Now let's look into the vertical asymptotes. When x is approaching minus infinity, in that case y approaches when x is approaching minus 90 degrees, y is approaching minus infinity in the graph of tan x. In this particular case, since there is a reflection, it is going to approach in the opposite direction, which is infinitely large, for x being half of 90 degrees, which is minus 45. So you can see very clearly that the period in this case has been reduced by half, and so it is, you can write like this also, minus 45 degrees, right? Minus of, um, actually from higher to lower values will do. So it will be 45 degrees minus of minus 45 degrees, which is equal to 90 degrees. So that becomes the period. So what we notice is that on the right side, when x is approaching positive 45 degrees, the y value is approaching negative infinitely large. So in this case, the transform function is actually going in the direction like this. Do you see that? Within the principal cycle which we are discussing, so the situation is kind of like this. This here is minus 45 degrees, correct? This here is plus 45 degrees, and you're approaching uh, to from positive infinity to negative infinity. So you have a decreasing graph in this particular case. The 3 points which we are talking about can be shown as A dash. So A is right here now, B dash and C dash, correct? The values being given there. Does it make sense to you, right? So that is how the graph is going to look. Since that is not a part of this particular question, we just made a rough sketch to give you an idea. Now let's move on and take example 2. In example 2, we will really sketch the graph of similar function, which is in this case y equals to 3 tan half x plus 1. Now I like you to pause the video, sketch this particular graph, and then look into my suggestions, correct? So clearly we see that first factor is 3, and that is a stretch factor. So value of a is 3 in our case. Then half is horizontally compressed by a factor of 2. So we write not like this, factor of 2. So it has become uh, horizontally, it is basically not a compression. Let me correct this. It is horizontally stretched by factor of 2. So that means that the period will be 2 times, right? So the period will be 2 times 180, which is going to be 360 as written correctly here. Now to map the points, the principle is taken as from minus 90 to plus 90. That is for the tangent function. In this particular case, they will be double the value, correct? So you can see that when we talk about the transform function, that cycle will be from minus 180 to plus 180, correct? Now, we'll actually analyze this particular cycle on the graph of tan x, and then see what happens to a transform function. So in this, we'll use the mapping diagram. The xy values will again begin with the A, B, and C point and find their images, correct? As we did last time. So we'll find A prime, B prime, C prime. The transformation clearly indicates that any point which is xy on the graph of tan function actually will be x values will get multiplied by 2 and the y values will get multiplied by 3, and then we are going to add 1 to them. So this is written right there. So when you multiply the x values by 2, minus 45 becomes minus 90. The y values multiplied by 3 and plus 1, in this case c dash will be minus 2. So these are the points which you are going to get, correct? Now let's look into the vertical asymptote. When x is approaching minus 90, y approaches minus infinitely large value. In this particular case, the x value gets multiplied by 2. So when x approaches minus 180 degrees, y approaches negative infinity. So that is our minus 180 degrees, correct? So in this graph, this is minus 180 degrees. So when x is approaching minus 180 degrees, the graph is approaching negative infinity. And that is our plus 180 degrees. One particular cycle we are looking, and the y value approaches positive infinity. Clear? The points A dash, B dash, and C dash are also shown here. A dash, B dash, and C dash. Correct? So these are the 3 points which are shown on the graph. The end behavior is shown to you. So that becomes our principal cycle, right? So this is our principal cycle. You can repeat this cycle to draw the entire graph of a tangent function in the given domain. So in this case, it is a general equation. So we just have drawn 3 cycles. As you can see here, repeating what we initially got. Perfect. So that is how you can easily sketch the graph of tangent function. Perfect. Now let's look into the next example, which is sketch the graph of another function. It is for your practice. So take this as a test question, correct? So let this be your test question. You need to now pause the video, sketch a very similar graph, which in this case is minus 3 tan half x plus 1, correct? So the only difference here is definitely reflection on the x-axis. Rest of the things are more or less same as we did last time. Now this reflection will actually make the graph decreasing, right? So now what you have is a decreasing function. Correct? So you can see that the graph is decreasing in the primary cycle and thereafter in every cycle, decreasing function in given cycle. Correct? Since it is a discontinuous function, we do not say in the whole uh, x belongs to real numbers, correct? We know there are discontinuities. So now you can look into this, which is very similar to the previous example. Treat this as your test question. Example 4. Write function of the form y equals to a tan kx plus q for the following graph. So now we are trying to figure out the equation from the given graph, right? So this is the reverse of what we did earlier. So now you have to do proper observation to get the solution. So let's now make a key on listing observation points. Now this is extremely important to quickly get the equation. So first thing is, we'll analyze the vertical asymptotes, correct? And see how far are they. So if you look at the vertical asymptotes, which are right there in red lines, dotted lines shown to you, the vertical asymptotes are at pi by 4 and minus pi by 4. So we have vertical asymptote at x equals to minus pi by 4 and also at x equals to pi by 4, correct? So these are the vertical asymptotes. So let's mark them. So this is one and this is the other. This is at minus pi by 4. So this graph is in radians and the other value is pi by 4. So that gives you the period. So the period will be difference between the two, right? So which is pi by 4 minus of minus pi by 4, correct? So when you do that, you get the value as pi by 2, correct? So pi by 2 becomes the period. So from here, you can find the value of k, which is the period. Uh, K will be pi divided by the period. And in this case, we know the period is pi by 2. So pi divided by pi by 2, that gives you 2. So we have found the value of k, right, in this particular equation using vertical asymptotes. So first value we have found. Now, so here's the calculation shown to you. Vertical asymptotes are pi by 2 apart, and therefore the period is pi by 2. So that is the distance which we are talking about. This is pi by 2 apart. And since p is pi by 2, k will be equal to 2, pi divided by p. Now, let's look into the transformed points. The point at the center, we had been calling this as B dash, correct? So point B dash. It is at minus 1. Let's write down the coordinates for point B dash. So B dash is the point which is moved to the value of minus 1, right? So the y value is minus 1. So that is b dash. Now this value of minus 1 actually gives you the value for q. So it is translated 1 unit down. You get the idea? Now let's look into the second point, which is a dash for us. Coordinates of a dash are at, in this particular case, pi by 8, we get the value at 2. So pi by 8 clearly indicates that horizontally there is a compression, right? Which we also got from the period, correct? So instead of pi by 4, if you compare this, instead of pi by 4, we get this point at pi by 8. That means that there is a horizontal compression, and that we found also with the value of k. So that part is okay. As far as the y value is concerned, what is 2 minus of minus 1? So 2 minus of minus 1 is 3. So therefore, we get the stretch factor A, which is 3. Do you see how we calculated the stretch factor? So that is how we are going to find the stretch factor. So now clearly, position of the center point B is 0 minus 1. So that means there's a vertical translation of 1 unit down. And the position of A dash is pi by 2, 2 is 3 units higher than B. So the difference between these 2 points here is 3 units, and therefore there is a vertical stretch by a factor of 3. So we get the value of A as 3. Now we can write down the equation 3 tan 2x minus 1. Is that clear to you, right? Combining the results which we have got from this analysis. So observation is that you have to find the vertical asymptotes, point A dash and B dash, to get the result. Clear? Now, we'll look into the phase shift part. So earlier we did not do phase shift. Here, we'll only concentrate on phase shift. So phase shift in tangent function. Y equals to A tan k x minus p plus q. The term p gives you the phase shift in this particular formula, right? So we are considering the formula y equals to A tan square brackets k x minus p plus q. It is important to note that k is always factored out. So therefore we are using different brackets all the time. So square brackets and within that x minus p in the normal brackets. So p is the phase shift. P is the phase shift. Now what does the effect of phase shift becomes? The whole graph moves left or right p units. That is what it means, correct? Phase shift. It is a horizontal translation, basically. So phase shift is horizontal translation. So P units, right? That is horizontal translation. That is the effect of P, correct? Now, what does the effect really is that you are shifting the whole cycle. So what really happens here is that the one cycle of y equals to this is actually speaking from minus 90 to plus 90, correct? Or minus pi by 2 to plus pi by 2. But one cycle of the transformed function now will be shifted, correct? P units to the right. So it is going to be from minus 90 plus p to 90 plus p. So what p really happens here, when you have a function here, then the vertical asymptotes will now at, if only transformation is this, a equals to 1, in that case, it is going to be 90 plus p, and this is going to be minus 90 plus p, right? So that is the effect. Basically, the whole cycle shifts, and that is the idea. So this is the cycle which shifts by p units to the right. That's what it is. Okay. That is when p is greater than 0. But if it is less than 0, it will be the other side. So based on this, here is an example. Write the duration of one cycle of tan x minus 15 degrees and provide its sketch. That is the question. So we have the p value of 15 degrees in this case. So what is the duration of the cycle? That is the question. So duration of the cycle for y equals to tan x minus 15 will be that we are going to add 15 to the cycle, principal cycle, which is minus 90 to 90. So minus 90 plus 15, and it goes up to plus 90 plus 15. So the cycle is from minus 75 to 105. So in the given example, this value is minus 75 and this value is 105. Correct? So that is how the cycle changes. So that becomes x equals to this first vertical asymptote, and the other vertical asymptote is at 105 degrees as shown in this particular graph. Perfect. So that is the effect. So it is shifted 15 degrees right. The graph indicates the same. Now let's take another example. The question here is graph of the function y equals to tan k x minus p is given to you below. So we have a graph in which there is a phase shift. Explain the phase shift and then write the equation of the tangent function. So we have to write the equation of a transformed function from the graph, and this function includes phase shift. So I'd like you to pause the video, answer this question, and then look into my suggestions. So how should we begin? We basically begin by finding the location of vertical asymptotes, these 2 points, correct? You get an idea. Now you can read from the graph what is the equation of this vertical asymptote. It is x equals to minus 3 pi by 4. And the other one is x equals to 5 pi by 4. So these are the two vertical asymptotes which we are looking at. So clearly, the difference between them is the period. So period will be 5 pi by 4 minus 3, a minus of minus 3 pi by 4. So it becomes positive, right? So you can calculate this period. So in this case, the period will be 2 pi. So this calculation is done. So what we are looking at is the duration of one cycle, which is from minus 3 pi by 4 to plus pi by 5 pi by 4. These are the vertical asymptotes. And period is their difference over just 2 pi. Is that clear to you? So once you get this period, in that case, you can actually find the value of k. So the value of k will be pi, which is the normal period, divided by the period p, which is 2 pi. And so the value is half. So we got the value of k as half, right? So that is how we get k. Now clearly the phase shift is what? Normally this should have been at pi by 2 minus and plus pi by 2. So the difference is the phase shift. Now phase shift clearly is by pi by 4. So so what we can do here is find the difference between 3 pi by 4. So phase shift P is difference between 3 pi by 4 and pi by 2, correct? So that should give you the phase shift. So once you do that, what do you get? You get the value which is equals to, let's do this. So it is 3 pi minus 2 pi by 4, and that is pi by 4, correct? So we have a phase shift P of pi by 4, correct? That is what it is. Now, easily you can calculate this phase shift from the point B itself, correct? So you'll have, so this is point A dash, B dash, and C dash, correct? So the point B gives you the horizontal shift in this case, since it is also on the x-intercept. Now the x value of this, you can see, is at pi by 4, correct? So B is basically at pi by 4, 0. So that gives you the phase shift, correct? And the vertical stretch, you can read directly from the y values difference between A and B. So this difference here between A and B is 1, and therefore the value of A is 1, right? So vertical stretch is not there, so 1. So therefore, we get from here our equation of the tangent function, which could be written as y equals to half of, which is the k value, half x minus pi by 4. You get the idea. And that is how we are going to write down our solution. So we get the equation y equals to tangent half of x minus pi by 4, correct? So I hope the steps are absolutely clear. So we incorporate this pi by 4 phase shift and then the value of half and got our equation. Perfect. So that is how you would get the equation of a transform function which includes phase shift uh, as shown here. Here's the last example. I would like you to take this as your test example, okay? Read the question, answer, and then look into my suggestions. Sketch the graph of y equals to half tan 30x minus 60 minus 1. Now, what should be your strategy? Now, whenever you are given a function like this, first step should be factor 30, right? So rewrite this. That is the important thing, correct? You remember using square brackets? So factor 30. So when you factor 30, you get half of tan 30 outside the bracket with x minus 2. So that 2 gives you the phase shift. You get the idea. Not 60, correct? So that is the first step. So always factor inside function. Always factor k value, correct? That is kind of important. So once you factor, then you describe the transformations beginning from the left side, so left to right. So the very first one here is half. That means vertically compressed by a factor of half. Then we have 30 horizontally compressed by a factor of 30, and that results into time period which is divided by 30, 360, oh sorry, uh, for tangent functions it is 180 by 30, correct? So for tangent function it is 180 over 30, which is the value of 6, correct? Okay, 6 is correct. However, 360 was wrong. 360 should have been 180. So let me just change this. Correct. Phase shift is 2 units as you can read, and it has been translated 1 unit down. Perfect. So that becomes the transformation. So each point now we'll consider the image mapping, correct? So for the given diagram, we need to sketch this x, y points. The x values will get divided by 30, the y values, and then in the x values, we are going to add 2, since that is a phase shift, to the right. Y values will be half minus half of original minus 1. So you get your transform function points. Label these points as your points A, B, C. So what you notice here, that the points actually come shift, there is a shift. So A dash, B dash, C dash are your points shown on the graph. It is always increasing since there is no reflection. and the graph will be as shown on the right hand side. Perfect. So I hope you have understood all the parameters. How do we get them and how do we sketch them? Perfect. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. So I'm leaving this for you to understand in details. In case there is any question, you can always write in the comments. Feel free to write an email to me if you really want to learn from me. Hope that makes sense. Thanks for your time and all the best.